We're continuing on lecturing here. We're going to lecture for a bit. We'll take a break, then do the exam there in lab time like normal. So last time we had a big day of gases there, so we are done with it hopefully. And so we're off to chapter 14. I think we're down to 2 more chapters after this, so not too bad. And then we'll just stare at each other for a few days. All right, so it's not too long of a chapter. We're basically going to talk about some properties of water, some intermolecular forces in this particular chapter. So let us get into it here. A little bit about water and its different sort of phases. Pure water is colorless, tasteless substance. Its normal sort of freezing point occurs at 0 degrees Celsius at 1 atmosphere, which is obviously a pressure. It goes into steam or the gas phase at 100 degrees Celsius, which is its normal boiling point. Liquid water happens really between 0 and 100 degrees Celsius. Really, it's not until you get, as we'll see here in just a sec, we might have talked about as well, not to really get, but just a little bit above 0 that you really do have the kind of pure liquid water. It's not until, you know, you're a little below there, 100, that you're still in liquid water. Right at those sort of transitions, as we will see, you know, you kind of have things in different phases going on between, say, solid, liquid, and gas. Water expands with its freezes. Water has some unusual properties. One of the most sort of unusual property of water is, unlike a lot of substances, in its solid phase, it actually is less dense than in its liquid phase. That is why when we put ice in our drink, right, it floats to the top. It is actually less dense. And as we'll talk about, really the reason for that is as water comes together in the solid form, it is held together by what is known as hydrogen bonding. But as these guys sort of bond to each other and you get a bunch of water molecules sort of freezing together, what it essentially does is kind of create a very big empty volume between the different water molecules when they come together. So unlike a lot of substances, when they get into the solid phase and everybody just really packs in super tight to each other, when water comes together, because of the hydrogen bonding, you actually get a lot of sort of empty space that involves between the different water molecules. And that's really important because if you think about sort of what density is, right? Density is mass divided by volume. So if we're creating all this sort of extra volume, the bottom number here is going to get larger, and the density of ice, say liquid water, will actually be less than what we would expect. So something like ice is like 917. Liquid water there, about 1 gram per milliliter is typically what we use for the density. And again, that is why sort of it will sort of float on top. Now, that's also why, right, when say water freezes, it actually freezes from the top down, right, not from the bottom up, and like on a lake or something like that. So what happens is you have your kind of your warmest water, which is like at 4 degrees Celsius, and that warm water will actually sink to the bottom. The colder water will float to the top where it will start to freeze, right? It'll start to freeze. And that's really good for obviously the life that's living underneath that ice, because they could still obviously swim around and not become popsicles, right, as the water freezes. Obviously, if it froze from the bottom up, that would be a different situation and so forth. So that's why, again, when like a lake or something like that freezes, you know, you got that layer of ice, which if you fall through, right, you're in the very cold water that's underneath there. And that's, again, because the warmer water will go to the bottom, cold water will go to the top, and it will actually start to make a layer of ice and actually insulate the bottom layer there from freezing at that particular point. Any questions on that there? Unless, of course, you go ice fishing and cut a hole in the ice, and then, you know, not so good for the fish. This is a heating and cooling curve for water, and we do see our different phases in water here. Down here, ice, which is obviously our solid phase. This is liquid water in the middle, and this is really the gas phase, right, of water there at steam. And this is our normal freezing and boiling point. Again, at 0 degrees Celsius, we see our freezing occurring. At 100 degrees Celsius, we see our liquid water going into steam. As I mentioned before, it's really not until you kind of get like a little bit above 0 degrees that you truly kind of get into the liquid phase. And it's actually not until you're a little bit below 0 degrees that you're actually in the ice phase. Dead on 0 degrees, we actually have an equilibrium that is there between basically the two phases. So we have basically like ice crystals happening. We got some kind of solid water. We got some liquid water sort of happening exactly at 0 degrees. So exactly at 0 degrees Celsius, basically both phases of water, for example, are in what is referred to as being equilibrium with each other. You basically have both phases occurring at the exact same time. We also see a very similar thing occur as we do the transition from liquid water to basically steam. At 100 degrees Celsius, you also have really both phases occurring at once. At 100 degrees Celsius, which is the normal boiling point, you have liquid going to gas and gas going to liquid. So both phases exactly in equilibrium with each other. Again, not to get a little bit above 0 degrees, it's really sort of transition into the gas phase, and not until you're a little bit below 100 degrees that you're still in the liquid phase. Again, exactly at that point, you have both things occurring. That's why our line here is flat at each of those spots. They plateau. There's no real change in temperature occurring at that point. This is also why, when you boil water and you got a thermometer, it only goes like 102. It should never really go over 100 degrees because it will start to boil right here at 100. And it's actually a cooling process that occurs when water or something boils, even though you think of it as like a hot process or a heating process. But you're actually cooling the solution from the top as you heat it from the bottom. And that's why when you hit something like 100 degrees Celsius, when it's technically boiling, it won't go any higher. And like, you're actually kind of cooling up on top and heating from the bottom, and it will be able to maintain that once it hits the boiling point. Sometimes people just freak out, like my thermometer only goes to 100, is it going to kind of continue to rise? And it won't rise because of that reason. Now, when we look at this sort of graph, obviously going from solid to liquid to gas, going in this direction, which is heating, we do need to put energy in to do that, and that is an endothermic process. And obviously heading in the opposite direction, going from gas to liquid to ice, which is our kind of cooling process. That is an exothermic process. All those are really exothermic. Again, as the steam loses energy, which is what exothermic means, giving off heat and energy, they slow down, they collide, they drop into the liquid phase. And obviously, as you continue to take heat and energy out, they're kind of clumping more together into the solid phase. Now, when we look at this curve, we also could apply something that we learned about in an earlier chapter, which was specific heat. Specific heat, which is Q is equal to ms delta T. And we use specific heat when we are talking about how much energy is involved in a process where something basically changes temperature, but remains in the same phase. So where something changes temperature and remains in the same phase is really what we use specific heat for, to figure out how much energy is being either absorbed or released in that process. And if we look at this sort of heating and cooling curve, that basically, for the most part here, is anywhere on this curve where we are kind of going vertical. These are all processes where if you want to know how much heat and energy was involved, you would basically use the specific heat equation. Remember, Q is heat and energy, M is mass, S is the specific heat capacity, which you want to make sure that you get for the proper substance in the proper phase. Delta T is the change in temperature, which is final minus initial. And remember that that temperature, unlike the ones in the gas law, is actually degrees Celsius. We leave it in, so we do that. And if you remember, as we talked about, this part is really important because that is where the negative comes from, right? initial, then it is going to be a negative value. That's important because Q that is negative, as a reminder, is an exothermic process. And if you calculate Q that is positive, that is a endothermic process. Any questions on that? So that actually leaves us, if we look at this, two places on this graph where if we want to know in terms of energy what's going on, there actually is a slightly different calculation that we do. And that's actually at these transitions that occur, these sort of phase transitions that are occurring here. So at these spots, there's actually a certain amount of heat that's required basically to do nothing more than change the phase of a substance, not change the temperature. Temperature doesn't move or anything like that, but solid to liquid or backwards, liquid to solid, or take something from liquid to gas and backwards as well. So down here, this is the energy that's required basically to take a substance from solid to liquid, like I said, or backwards, liquid to solid, without changing the temperature. So that would be at its normal melting point or freezing point. So for something like water, that would be at 0 degrees. Again, because it plateaus at those transitions. Heat of fusion. We will see the heat of fusion here in just a second, I think, on the next page, and we'll take a look at it. But for water, the heat of fusion is 333 joules per gram, give or take a joule. We also have a transition that occurs up here from liquid to gas, and the energy required to do that transition is what is known as the heat of fusion. I'm sorry, not heat of fusion, heat of vaporization. So the heat of vaporization is the energy required to take a substance from liquid to gas and backwards, gas back to liquid. And roughly speaking, for water, it is roughly 2260 joules per gram to do that. Which one takes more energy to do the transition? It is the transition from liquid to gas, right? Which takes about 2260 versus about 333. And that's because if you just think about the different phases as you go from solid to liquid, solid, everybody's pretty close to each other. When you go to liquid, everybody's still relatively close to each other, but they have more room for movement, which is why liquids obviously are fluid. But when we do the transition of going from liquid to gas, everybody needs to really completely separate from each other, right, into the gas phase as they're flying around. So it takes a lot more energy to get everybody completely apart from each other so that they can enter the gas phase and start flying around. Any questions on any of that graffitied up diagram here? All right. So let's take a look at that, I think. So as I mentioned before, there are two types of bonding that occurs and sort of the energy required to change them. And we'll talk a little bit more about these in just a second. But the bonding forces that basically hold a molecule together within the molecule are what are known as intramolecular forces. And the forces that hold basically one molecule together with another are intermolecular forces. And as I mentioned before, which is just basically the mole version of what I put on the board there for the transition between, again, this is basically your transition of solid to liquid or backwards, is 6.02 kilojoules per mole, which is the same, roughly 333 joules per gram. And to go from our liquid to gas and backwards, that is 40.6 kilojoules per mole for water. And again, that roughly equates to about 2260 joules per gram. So again, how do those two sort of calculations tie together? Let's just say if we took a look at we'll go next page. So let's say we had let's say we had like 225 grams of steam at, let's say, 105 degrees Celsius. How much energy is needed to be released to get 225 grams of ice at, let's do minus 200, not minus 200 now, minus 2.5 degrees Celsius. There you go. Okay. So we could kind of go through this problem, and we could use, again, our specific heat and our heat of fusion, our heat of vaporization to help us out. So if I just roughly sort of sketch that diagram we were looking at before. And again, if this is ice down here, this is about 0 degrees. This is about 100 degrees. And obviously this is liquid water, and that is steam. So if we follow along sort of where we're starting at 105 degrees, which roughly we will say is about here. So the first process that would actually happen is that steam that's at 105 degrees would basically come down to steam at 100 degrees Celsius. So when we think about what is happening at this point, all the way through here, this is steam, which means we are changing in the same phase. And again, this is not a plateau line on this graph, which means we want to calculate the heat using specific heat equation that we talked about before. So the first thing that would happen would be our Q is equal to ms delta T. Again, taking it from 105 to 100 degrees Celsius. Putting in our numbers here, we would use our mass, which is 225 grams. Now, it's really important here that we actually use the specific heat capacity, not a liquid water, which is that 4.184 number that we've used a lot, but we want to make sure that we actually use it for steam, which I can't remember off my head. So I'm going to go with it is about 201 joules per gram per degree Celsius. We'll just say that is for steam. And we'll use that number here. And now remember that our final temperature here is actually 100 and our initial temperature is 105. So I'll run out of room, so I'll write it underneath 100 minus 105 degrees Celsius. So for the very first sort of transition that we're doing, it would be 225 times 2.01 times 100 minus 105 is I believe it is 2261. I think that's a comma on my calculator. So as a minus, I think. The units here would be joules. So that is the amount of energy that's required just to do basically that transition. Any questions so far? The next thing that would happen is now we are sitting basically at steam at 100 degrees Celsius. We would need to transfer from steam to basically liquid water at 100 degrees Celsius. So that would take us here, and this would be our second step. So in this particular changing the phase, the vaporization would come into play. So this would be our heat of vaporization. And if we wanted to calculate the heat or energy required to do that, that would be our 2260. And again, that is specific, obviously, for water. If you're not talking about water, it would be a different heat of vaporization. So we would take the mass of 225 grams. This would be 2260 joules per gram. And should this number be positive or negative? It should be negative, as this is an exothermic process, right? We're releasing the energy here as we go backwards. So actually, this should be a negative number to match our other negative number there. And that gets us 225 times 2260 gets us I believe it is 508,500 joules, which would be negative in this case. Any questions so far? Okay, the next thing is we're now sitting basically at 100 degrees liquid water. The next sort of transition that will occur is that liquid water will essentially be cooled down from 100 degrees Celsius to 0 degrees Celsius. So in this particular process here, we are changing the temperature, but we are not changing the phase. So it's liquid all the way through that process. So this once again would take us back to our specific heat equation. And that would get us, I'm gonna flip the page here, just have somewhere to write for number 3. 100 degrees Celsius, liquid water to 0 degrees Celsius. We would use this case. Our final temperature is actually 0. Our initial temperature is 100 degrees Celsius. And again, that is where our negative is going to come from. And do that 25 4 times 100 gets us 94,140. And that would be how much energy would need to be released as this basically water is cooling down. Any questions so far? All right, so we now find ourselves sitting right about here, and we are at basically 0 degree liquid water. That's going to occur is we are going to go from 0 degrees liquid water to 0 degrees ice, basically. Will be our fourth transition. Once again, at this point, we're not changing the temperature, but we are changing the phase. And this would be our heat of fusion where we would want to use here. So using our heat of fusion for our calculation gets us our fourth process going from 0 degrees liquid to 0 degrees ice or solid. And our heat of fusion, again, specifically for water, if you're using some other substance, once again, it would be a different value. We'll just use 303 joules. Process occurring here gives us 225 times 333. Gives us negative 74,925 joules. So obviously we can see here it took about 72,000 joules to do the transition going from liquid back to solid. It took about 508,000 joules, right, to do the transition of going from gas back to liquid. So a lot more energy involved in that process. We're almost done, and we would have been if I hit 0, but I went for negative 2.5, which would put us right about there. So we have one last little spot to drop down to, which in this case would be from here to here, basically. And that would be the fifth and final step in this calculation here. Number 5. That is again going from ice at 0 degrees to ice at minus 2.5. And that again is temperature. So once again, we use our specific heat for this last move. And that would be going from 0 degrees ice to minus 2.5 degrees ice. And Q equals ms delta T, and that would give us our mass of 225. Once again, here we would want to use the specific heat capacity for ice, not liquid water. We'll go with 2.1 joules per gram per degree Celsius. Could only be off by a little on that guess. So this would be our final temperature, which is minus 2.5, minus our initial, which was 0 in this case. That again is where our negative is going to come from. That's going to give us 2.5 times 2.1 times 225. Gives us like 1181. We'll round it to. Could figure out the total energy by going back basically and adding up all the energy required for each of the individual steps here to get our total amount of energy, which would be this guy and this guy. So if we do that, we end up with, roughly speaking, 2261 plus 508 500 plus 94140 plus 74925 plus 1181. Roughly total energy, just add all. It's your minus 681,007 joules, or roughly minus 681 kilojoules is released in this process. Any questions on any of those steps in those calculations? So really it's very much just using our specific heat equation and our heat of fusion, heat of vaporization kind of added in there. And again, if you're in the same phase but change temperature, always specific heat. If you are different phases, same temperature, should be a heat of fusion, heat of vaporization sort of calculation. And again, heat of vaporization, heat of fusion will change depending on the substance. Again, those numbers are specific for water. Yes. What's that? You good? Okay. Other questions? Okay. So then let's talk a little bit about the intra and intermolecular forces. So a second ago, we saw that there are two different sort of forces that we talk about. One is the intramolecular force. And that is actually the force that holds one molecule together, not with another molecule, but just one single molecule by itself. So if we look at like the water here, it is really the bonds there between the oxygen, hydrogen, the covalent bond, the sharing of electrons. Those are the intramolecular forces. The intermolecular forces are the forces that hold one entire, say, water molecule together with another entire water molecule, and it is this bond right here between, in the case of water, the oxygen and the hydrogen. That's an intermolecular force. Intermolecular forces are always weaker than any intramolecular force. We know that simply by making water and boiling it. When we boil water, it is this bond right here that breaks first, which is why we get obviously water into steam, which is in the gas phase. If it was the opposite, like I might have said before, you would produce hydrogen gas and oxygen gas if you went to go boil water, and that would probably not be good. So intermolecular forces are always much, much weaker than intramolecular forces. Strongest intramolecular force really is electrostatic attraction. This is the force that we see in ionic bonding between the positive and negative ions. Very, very strong. Covalent bonds is also an intramolecular force, but kind of the strongest one is that kind of electrostatic attraction between opposite charged things. We're going to talk here about intermolecular forces, and there are a few different types of intermolecular forces that we're going to talk about. And I think it's on your slide, the next one. So I'll just kind of write it out and kind of explain some of these as we go through them. But the first one is what is referred to as a dipole interaction. And again, these are all intermolecular forces we're talking about here. Dipole interaction is, if you remember, we've seen the word dipole before when we're talking about bonding. And typically things that have dipoles have what are referred to as dipole moments. And those are basically polar molecules, are guys that have those. So if you remember, polar molecules have overall an unequal sharing of electrons. And what that creates in a polar molecule is a side of that molecule that's more positive and a side that's more negative as a result of those unequal sharing of electrons. And the dipole interaction is pretty much the strongest intermolecular force that occurs when two polar molecules basically come together. And that is because basically, if you have a polar molecule, this guy has a positive negative sign. And another polar molecule will also have a positive and negative. And it is the interaction between the negative side of one and the positive side of another molecule that is what is the dipole interaction. Truthfully speaking, all intermolecular forces are nothing more than positive negative attraction. That's basically how they all work. So this is a type of intermolecular force that occurs. We see different variations of this. Sometimes this is what happens when we dissolve water, some type of ionic compound in water. We get something that's sort of known as an ion dipole interaction. Ions obviously have charge. Dipole, guys, obviously is a polar molecule that has a charge and is the negative attraction there. Again, when we drop something like an ionic compound in water, the positive ion gets surrounded by the negative side of like water, right, which is negative. So that's what happens. And the negative ion gets surrounded by the positive side of water, which is actually the hydrogens, and they surround each of those guys. And again, that is how something dissolves its ionic in solution. And that's sometimes referred to as an ion dipole interaction, which is similar to dipole interaction. A special type of dipole interaction is one that is known as hydrogen bonding. And it is a relatively strong dipole interaction, kind of the strongest you could have. And that is a bond between hydrogen and an electronegative atom like nitrogen, oxygen, and fluorine. So if you look at the periodic table, that is your big three there, running into fluorine, which is the most electronegative, nitrogen, oxygen, fluorine. In order to have hydrogen bonding, the hydrogen needs to be directly bound to nitrogen, oxygen, or fluorine. The reason for that is the difference in electronegativity is going to create quite a polar bond, and that's going to allow it to interact. That is actually what we do see in water. Water, which is a polar molecule where the oxygen is more negative, hydrogen is more positive. So when one water molecule basically interacts with another, which also is negative and positive, the negative side of one, which is the oxygen, is attracted to the positive side of another. And that is what is known right there as hydrogen bonding. It is really a very strong interaction that occurs. So when we think about dipole, it is usually reserved for polar molecules that cannot hydrogen bond. So if you're asked sort of what is the intermolecular force for a polar molecule that doesn't have the ability to hydrogen bond, dipole is your answer there. So this is really polar guys, no ability to hydrogen bond. If you have a polar molecule like water that has the ability to hydrogen bond, then hydrogen bonding is really the strongest, even though technically it is still dipole-dipole, but you would classify it as hydrogen bonding. Now, just because something has hydrogens, it does not mean it can hydrogen bond. Could something like CH4 hydrogen bond? And you may be tempted to say yes, because there's a ton of hydrogens. But a couple of things here. First off, that hydrogen, none of those hydrogens are bound to nitrogen, oxygen, or fluorine. And besides that, CH4, is that a polar or non-polar molecule? It is a non-polar molecule, right? So even though it has a ton of hydrogens, it does not have the ability to hydrogen bond. So sometimes people think you just need hydrogens present, but it needs to really be a hydrogen is attached to one of those guys that creates that separation, so they could do the positive negative sort of attraction to each other. Any questions on those guys there? So what does something like CH4 use? It uses what is sometimes referred to as dispersion forces. Dispersion forces are pretty much for our non-polar molecules. So non-polar molecules basically use dispersion forces. And you may say to yourself, if something is non-polar, it means that they are sharing the electrons equally. There's really no positive side or negative side to that particular molecule. And that is true. So with dispersion forces, these are really weak, temporary forces that occur. So how could they occur? Well, occur in a couple of different ways. They could be induced. So you could have a induced dipole. So what does that mean? It means that if you have a non-polar molecule that really has no charge and a polar molecule comes up on it, temporarily what's going to happen is this positive side of the polar molecule is going to do what to the electrons in this guy? They're going to be attracted to it, right? Because opposites attract. So what will temporarily happen in our nonpolar guy is it will temporarily gain a charge. And now it has a temporary way to interact with one another. So our nonpolar guy will temporarily gain a charge. It is temporary because as soon as the polar guy kind of moves away a little bit and those electrons shift back, there goes the interaction. It's not going to hold very long. It's kind of the idea of like, for example, like oil and vinegar salad dressing or something like that, right? You mix it and stays mixed for a bit, right? But eventually over time, everybody separates out. It's a sort of bond that it can't be maintained over a long period of time. Now, what happens, another way that you could do that is simply you could just have, for example, two nonpolar molecules and electrons are flying around. And for some reason, if in the first guy, all the electrons decide, let's just all go this side for vacation. What's going to happen is this first nonpolar molecule will then become temporarily charged. And if he's still sitting next to the other nonpolar molecule, the electrons in this guy is going to go, whoa, negative, I want to go away. And this guy will then get a temporary charge. And now both of these guys, which started out with no charge, both achieved a temporary charge and a way to interact with each other. This is what is known as polarizability. And that is the ease at which electrons can move around. And again, this is temporary because as soon as the electrons decide to go back, it's going to break apart. This guy will have a new interaction with somebody next to him. It'll break apart and so forth. So these are very temporary sort of ways of things that normally do not have charges to gain charges, and they have a way to interact with each other. Dispersion forces increase. strength with increased molar mass. So the higher the molar mass, the stronger the dispersion force will be. That's like a double sentence there. So speaking specifically for dispersion forces, more higher molar mass, stronger the dispersion force will be. The reason for that is if you have a higher molar mass, you most likely have more elements involved. More elements involved mean more electrons. More electrons means it's going to be a lot easier for those guys to kind of move around and create these temporary charges and interact with each other. Question on any of those intermolecular forces. So the strongest of those intermolecular forces is hydrogen bonding, followed by dipole-dipole, followed by the weakest, which is dispersion forces. And again, this is really for polar guys that can hydrogen bond. This is really for polar guys that cannot hydrogen bond, and for non-polar molecules. That's basically how they interact with themselves or other guys that are very similar. So something like NH3, what would be the major intermolecular force that would this guy use? NH3 is polar, right? It's got dots and basically 3 bonds. So dots, everybody's saying it's a polar molecule, but it also has a bond between nitrogen and hydrogen, which means it can hydrogen bond. That's basically what you need. If you had this guy, polar or non-polar? This guy's polar, yes. Can it hydrogen bond? It cannot hydrogen bond because that's a carbon, right? So that's where the hydrogen. So it would use to dipole-dipole interaction. And lastly, like this guy would use dispersion forces. Yeah, it's non-polar all around. It'll use dispersion forces. Now between this guy and this guy, which one would have the stronger dispersion force? It would be this guy. Yes, more guys there, more atoms, more electrons, stronger the dispersion force. Any questions on any of those intermolecular forces there? And that's pretty much what's on this page here, what we just talked about there, I think. London dispersion forces are relatively weak forces that exist among noble gases and nonpolar. Again, they're sometimes called London dispersion forces. All these guys together are also sometimes called van der Waals forces. But they're basically how one molecule interacts with another. These are all intermolecular forces that we talked about. Why is that important? It's important to what we just talked about. The stronger the intermolecular force, the higher things like boiling points are and melting points. The weaker the intermolecular force, the lower the melting point and boiling point. So these boiling point increases, melting point increases with stronger intermolecular forces. Weaker intermolecular forces have lower boiling points and melting points. That is why if you ever know about organic molecules, which are things like methane, propane, butane, you know, those are all pretty much gases, right? And they're all pretty much non-polar. They all use dispersion forces, which means they go into the gas phase relatively easy for one another. So things that jump into the gas phase relatively easy, things that are what are sometimes referred to as being volatile, which will go into the gas phase relatively easy, usually have very weak intermolecular forces. They could just simply break apart really quickly. if you ever take organic chemistry, most of the stuff you deal with are very volatile like that because they're non-polar and they can kind of break apart really quickly into the gas phase, which is why they stick you in a fume hood when you go do or work at organic chemistry, so you don't smell all that stuff that's basically in the gas phase. Any questions on intermolecular forces there? There's some pretty pictures or than more than what I draw, but the basic interaction of any intermolecular force really is that electrostatic attraction between the positive and negative. By the way, they do in the solid and liquid phase, you know, just by how much are there and how close they are to each other, you are going to get some negative things near negative things, which is not good, and positive sides of guys near positive sides. But they really do try to keep moving around until they find a spot which they kind of maximize the attractive forces and sort of minimize any repulsion force that may occur between molecules. Here's hydrogen bonding. And again, as you can kind of see in this picture, it starts to create these really big volumes between the water molecules. And again, as we talked about earlier, that's why we see a lower density in something like ice. This is what is referred to as an instantaneous dipole, which is what I was talking about. Again, two non-polar guys that don't have a separation in charge. Just by those electrons kind of moving from one side to the next will create a temporary charge, and again, a temporary way for those guys to interact with each other. And at some point, everything will go back to normal. Pretty much everybody could do some type of dispersion forces. So even polar molecules could do some type of dispersion force, but it's not really their major way of interacting. And that's why we get those kind of temporary interactions that occur between polar and non-polar molecules. You know, they can kind of hang with each other for a bit, but eventually they will sort of not be able to maintain that overall. The major difference between sort of dipole and like a dispersion force is no matter what happens with a polar molecule, it's good to go. It always has that separation of charge. It's never going to lose the separation of charge, which is why it's a much stronger interaction than dispersion forces, because dispersion forces rely on temporarily getting these differences in charge. So because polar molecules are locked into place, they'll never lose that. Any questions on that there? Okay. So we talked about vaporization, evaporation, which obviously is the process where we go from liquid to gas and backwards. Obviously, condensation is the process going from liquid back to gas. The vapor pressure of a liquid, as we talked a little bit about gases last time, is really the vapor that occurs above the liquid phase. Liquids with high vapor pressure are said to be volatile. They will evaporate really quickly, and it is related to intermolecular forces. So when you have a liquid at the surface of any liquid, there is a constant exchange of guys jumping out of the liquid into the gas phase and slower moving gas molecules that basically will drop back into the liquid phase. So at the surface of any liquid, that's what happens. That's also why when you spill something like on a bench or something, right, a little bit of water, if you just leave it, eventually it will evaporate off. You have a rate of evaporation happening, and you also have guys dropping back in. But what happens though is there is air which pushes those guys out of the way, and you get less guys dropping back into the liquid, more guys evaporating. So the rate of evaporation increases, and eventually your puddle there that you made there on the bench will evaporate off. It takes longer to do, right? If you put some liquid in a beaker, right, it takes longer for that to evaporate off, right? Because there's a lot more water molecules trapped at the bottom. So you got to work your way through most of that, and it takes a lot longer to do so. So when this happens, though, at the surface of a liquid, when those guys basically jump out into the gas phase, you do have steam or whatever may be above it. And that is obviously going to create pressure, right? Because they are gases that are above the liquid. And that is what vapor pressure is. And if you look at a container that has a liquid in it that's closed, when you close this container, you eventually start to have a very quick rate of evaporation that's occurring. But because this container is closed, those guys pretty much have nowhere to go, right? So they are going to start coming back down into the solution as they slow down. at some point, the solution will come to equilibrium. And what you typically will see is if you close a container, the liquid volume will actually drop a little bit. And that's because initially you have all liquid, then you got that process of evaporation that's going to bring the liquid level down, and then some will come back, and eventually it'll come back to equilibrium, which means the rate at which they are coming down will equal the rate at which they are leaving this solution. It doesn't mean you have the same amount on both sides. It just means obviously the rate will equal. And typically what you'll see is in a closed container, liquid volume will decrease a little. All these sort of gas molecules above the liquid is what's causing the vapor pressure. And things with very high vapor pressures are volatile. They go into the gas phase really well. It's a very simple concept. The only way to get a lot of pressure is to have probably a lot of gases, right? And the only way to get a lot of gases is a lot of those guys have now evaporated off from the liquid phase. And obviously, it would evaporate into the gas phase really, really quickly. So you'll have a lot of gas molecules over the liquid. Any questions on that there? All right, well, that was fun. All right, let's take a break.